Hello. What do you call a cold dog? It's a chili dog. It's chili. Brr. Okay, so we've got another video. Today we are talking about continuity. Okay, in particular, we're going to be looking at these things called piecewise functions. They're, yeah, we'll talk about that in a moment. Continuity, it sounds exactly how it is, like by little infinity. There's no break in the function. Okay, we use it later to prove if something is differentiable. And when we talk about continuity, we normally talk about the x values. Okay, now, as a quick little example here, if we take a look at these two graphs, we can see the graph on the left has no breaks. So if there's no breaks, we say it's continuous. All right, now if we take a look at this one, we can see here that there's an actual break in this graph. So we're going to say it's discontinuous, but only at a certain point. And it's discontinuous at the point where x equals 2. So that's what we would write. You see here, there's no breaks. So it's continuous all the way through for all x. But here, our function here has a break at x equals 2. If not, it's continuous everywhere else. Okay. Hopefully that makes a bit of sense. Now, piecewise is probably where we're going to spend the most time here. And it's just a function that's made up of pieces. Okay, now what I note here, and I don't see a lot of people talking about, I like to call it, there's points of interest in all these piecewise functions. Okay, so for example, a piecewise function, it kind of looks a little bit like this. So we kind of have a singular function that's made up of different pieces. Okay, now we can see here that the point of interest is actually something happens at x equals to 0. Okay, so our points of interest, I'm just going to highlight them here. I can see here that something definitely happens at x equals to 0. That was a horrible x. And for this graph down here, we can see that there's something that happens. Oh, it kind of disappeared on me a bit. But we can see here that there's something that happens around this -1. And we also see that something kind of happens around this 3 mark. Okay. Now, as we go through the examples, you'll see exactly what it means. Oh, of course, it disappeared. Let's actually draw one of these so we can actually see what it looks like. Now, I'm just going to finish this off. Let's say, for example, this would be, let's do something as simple as x squared for x is greater than or equal to 3. Okay, so we can see that there's two things that happen. Now, for me to draw this graph, I'm just going to draw it like this. And I'm going to note a couple things. I can see that something happens here at x is -1. So there's something that happens here, and I'm just going to note it down like this. Let's just do that. Be a bit easier. And then that's something that happens at 3. And then what it's saying here is for x is less than -1, which is this whole portion on this side, we see here that we're actually working with x plus 2. So usually that'll be a graph that looks like this. Okay, now I'm going to dot it from here to here, but then from here on, and again, we can't equal it, so I'm going to leave the circle open. Okay, so it's going to look a little bit like this. Okay, so from -1 to the left, we have that graph, which is x plus 2. Okay, but then we kind of stop there, and then between -1 and 3, we kind of have this exponential of 2 to the power of x. So in between here and here, all right, I'll kind of maybe highlight it so you can see, we've got I know it's supposed to be let's try my best here. It'll be something like this. Okay, now I can equal at -1 because I can have that equal sign, so I'm going to color it in. And then all the way at this point 3, it's going to end up with an open circle. And then from there, it's going to be x squared for x is greater than 3. So it would be a parabola, but it's actually going to start at, if this was 8, the parabola for, let's pick a different color again, for x squared would be something like, so it'll start at 9 and it'll kind of continue all the way up. Okay, all the way to the right. Now, can you see how this function here, it's made up of a straight line when x is less than 1. It's made up of a exponential between -1 and -3. There's our exponential. And then for x is greater than 3, we've just got this part of the parabola. So if I was to draw the whole parabola, it would have come down, look a little bit like this, but I'm only restricting certain things to within a certain domain. Okay, so the red part is the linear, the blue part is the exponential, and I guess that last little curve part is just the last part of the exponential. You can see here, this is discontinued. So we say that this graph is discontinuous at the points x equals -1 and x equals to 3, right? Because they've definitely got a gap. These two aren't the same. If you wanted to, the way that you would prove it is you'd say what happens x plus 2. So at x equals 1, something happens. X plus 2 would actually just equal to 3 when x equals to 1. But 2 to the x would actually equal to, oh, sorry, at x equals -1. So if it was -1, it will be negative, or I'm really struggling here, 1, right? Because -1 plus 2. So here, plus 2, that would be 1. And then 2 to the x would equal to a half. So we see here it's not continuous. And then we can do the same thing for x equals to 3. We can test it for 2 to the x, which would be 2 to the 3, which is 8. But then for the other one, which is x squared, you're going to have 3 squared, which is 9. We see here that it's also not continuous. It's close, but not quite continuous. Okay, so we would say it's not continuous at those points. So I would prefer the graphical method because it's helpful to know what it looks like, but then you can also prove it algebraically and test whether things are continuous or not. Hope that helps, and I'll catch you in the next video. Bye.